Good afternoon everyone. Today we will talk about heat transfer via conduction. Let's start with the definition of conduction. Conduction involves heat transfer from one point to another in physical contact without appreciable displacement of molecules. Suppose you have a body at high temperature and another body at low temperature. If you join them, the heat is expected to flow from body at higher temperature to body at lower temperature. This is the consequence of second law of thermodynamics. Now, conduction is enabled by molecular collision or transfer of energy. No large scale movement can occur. Usually it happens in solids and less in liquids and rarely gases. Take example of metal rod being heated by a burner from one end, another end remains cold. As the temperature increases from one end, let's assign it a temperature capital T, and let's assign a temperature small t, capital T being small greater than small t. So heat is naturally going to flow from higher temperature to lower temperature. Conduction is the process of heat transfer from one point to another in physical contact without appreciable displacement of molecules. Suppose you have a body at higher temperature, say T hot, and a body at lower temperature, say T cold. Heat is naturally expected to flow from higher temperature to lower temperature as long as this temperature difference exists. If you join the body, it will naturally flow. This is governed by second law of thermodynamics, and heat will continue to flow as long as there is a temperature differential. When temperature of both bodies become equal, that is, the temperature of hot body decreases and the temperature of the cold body rises. When the temperature of both bodies become equal, then the heat flow stops. Heat is expected to flow as long as the temperature difference exists. This process is governed by a law called Fourier's law of heat conduction, which states that at steady state, heat transfer through a homogeneous and isotropic solid is directly proportional to the temperature gradient and area of cross section. Suppose rate of heat transfer per unit time is taken as Q, measured in watts. This end is hot end and this end is cold end. Expect this being the higher temperature T1, this being the lower temperature T2. We are taking T1 greater than T2. As the temperature differential exists, it is expected to flow and across the length. Let's take this as the length dx, considering it to be extremely small. If it were larger, we could have taken, say, suppose L. If the body is assigned a name A, we can take it as LA. Now the temperature differential or temperature gradient can be measured as dt by dx, and the area of cross section is this one here, this one here. It naturally flow from this end to that end because the temperature T1 is greater than T2. Now the rate of heat flow is also proportional to area of cross section, so we can mathematically write Q equals to minus Ka dt by dx, K being the thermal conductivity, a property of material to conduct heat. The negative sign is there to account for the negative nature of thermal temperature gradient. As heat flows from higher temperature to lower temperature, we measure temperature gradient from lower temperature to higher temperature. So expect this term to be always negative, less than 0. To negate the effect of this term, we use a negative sign, and therefore eventually the rate of heat transfer comes out to be positive. If you have a body at higher temperature T hot and another end of the body being at lower temperature T cold, we can write the equation for heat flow via conduction using Fourier's law as Q equal to minus Ka dA hot minus T cold divided by length through which the heat flows. Also it can be written in differential term equal to minus Ka dt by dx. Assuming SI units are taken, rate of heat flow Q is taken in watts. The surface area of cross section measured perpendicular to direction of flow can be measured in meter square, and and the temperature differential can be measured in centigrade or Kelvin. As we are taking SI unit, we are taking Kelvin here. The length dx or L can be measured in meter. Now, one important thing, the area must be measured perpendicular to the direction of heat flow. If you take example, the body, let's take a look at this graph. Expect heat is flowing from the hot wall to the cold wall. This is the cold wall. See, as heat flows from this wall to this wall, temperature drops from T1 to T2 to linearly. Okay, this is one consequence of Fourier's law. Q is linearly proportional to the temperature gradient. So, whatever temperature differential exists, T1 minus T2, it must decrease linearly. So, as heat flows from this wall to this wall, the area of cross section is measured perpendicular. This is measured perpendicular. That is what is being said in that definition term here. Next, let's look at some of the assumptions used to apply this law. The steady state condition of the system must be maintained. This is self-explanatory. Next important thing is unidirectional heat flow. As explained by second law of thermodynamics, heat is always expected to flow from higher temperature to lower temperature. The other side, the other way is not possible. That is, heat cannot flow from lower temperature to high temperature. This is what is being written here. Unidirectional heat flow. Heat will flow from very high to T low. The temperature gradient is constant and temperature profile is linear. I explained this earlier. Due to the linear proportionality, the temperature must drop linearly. Next is no internal heat generation. Take example of nuclear reactor. Because nuclear reactor produces a lot of heat inside, we cannot use Fourier's law, because one of the assumptions of Fourier's law is no internal heat generation, that is no heat generation inside the system. There is one equation called Cantilever equation which is used for that type of situation, but that's out of syllabus. Next is isothermal surface temperature must be maintained throughout the heat flow period. This is self-explanatory. Next is property of material being governed by the homogeneity and isotropicity of the system or the material or the body used. Homogeneous and isotropy means the properties such as thermal conductivity, density of material, specific heat of material. These kind of properties are expected to remain constant throughout the body. These are some of the applications of Fourier's law: engineering design, building insulation, climate control, manufacturing, thermal management, geothermal. Manufacturing and engineering design are somewhat hybrid. Fourier's law is used or applied to measure the rate of heat flow of various materials and design systems accordingly. Building insulation is one of the major applications of Fourier's law, where to isolate or insulate the building from higher temperature during summer or lower temperature during winter, we can use Fourier's law throughout the wall and design insulations accordingly. For climate control, suppose as air conditioning, we use Fourier's law to accurately measure the temperature inside and outside. Using that temperature differential term, we will learn more about it while we are solving some examples later. Next is thermal management. This is also one application in industries and manufacturing. Another unique application is while exploring geothermal energy, we can use Fourier's law to explore various geothermal energy sites. Now let's look at a composite system containing 3 walls. All these walls at steady state, isotropic material and homogeneity of system is maintained. We will apply Fourier's law. Heat is being conducted from the inside the wall to the outside by 3 layers with different thermal conductivity and maintained at different temperature. The inner wall, let's say, is being maintained at temperature T1. The layer between the inner wall and the next wall is being maintained at temperature T2. The middle wall and the outer wall, the layer between, let's say, it's maintained at T3, and the wall is going outside. Let's say the temperature is maintained at T4. Assume the thermal conductivity of all 3 wall materials are K1, K2 and K3, and the length of the wall, let's take it as LA for the first wall. For the second wall, we can take the length of the wall to be LB, and for the third wall, we can take, let's say, we take it as LC. The area of cross section, let's take a clearer look at the area of cross section before we delve into the detailed explanation of different processes. This is the area of cross section. Okay, heat is expected to flow from here to here. The area of cross section is measured perpendicularly. So area of cross section will remain same. Now, because the heat flows from this wall, the inside wall, to the middle wall and to the outer wall, the rate of heat flow to the first wall must be equal to the rate of heat flow through the middle wall and then the rate of heat flow to the outer wall. This is a diagram representing all the conditions, temperature and parameters we discussed. These are the wall thicknesses, these are the thermal conductivities, and these are the temperatures T2 and T3 for the inner wall interfaces. These are the term descriptions. We already discussed them, and as we said, the heat flow to first wall is equal to that of the second wall and third wall. Now, applying Fourier's law, we can write the heat flow to first wall is Ka dot A, that is area of cross section, into temperature differential T. These are supposed to be T2 minus T1. If you are taking the temperature gradient, what we are taking the temperature differential here, and here T2 is the lower temperature, is less than T1. So the negative term is not there, that is self-explanatory. So using Fourier's law, the rate of heat conduction through the first wall comes out to be Ka dot A T1 minus T2 divided by length of wall LA. Similarly, we can determine the rate of heat flow to the second wall and the third wall. Now we can generate 3 different equations for the temperature differential in all these 3 walls, isolating the other terms to the left hand side. We can write to the first wall the temperature differential equals Q dot length of the first wall divided by thermodynamic conductivity of the first wall dot area of cross section. Similarly, the temperature differential of the second and third wall are written here. If you take sum of the left hand side and sum of the right hand side, you can write sum of the left hand side as T1 minus T2 plus T2 minus T3 plus T4, T3 minus T4. Here T minus T2 plus T2 cancel out, minus T3 plus T3 cancel out. So this can be written as sum total T1 minus T4 minus T4. This must be equal to the sum of this side, that is, here we can see Q is common, so we can write Q common, taken common, LA divided by KA dot A plus LB divided by KB dot A, area being the same for all 3 walls, plus LC divided by KC dot A. To measure the rate of transfer through the opposite wall, we can divide this term to the final temperature differential and write this equation as Q equals to D1 minus D4 divided by the total resistance. Here the first term being the resistance offered by the first valve, the second one offers resistance RB, and the third one offers resistance RC. This is the final equation for rate of heat transfer through a composite valve. As you can see, even though the temperature thermal conductivity of the materials used for the valves are different, we can still measure the rate of heat flow through the composite valve. Suppose in case of 3 valves there were n valves, we can write the final temperature rate of heat flow as T1 minus Tn plus 1 divided by sum R n for n valves. Here it is taken n plus 1 because for 3 valves while we are calculating the valve exposed to atmosphere at temperature T4, that is 3 plus 1. So if you are taking n valves, then the temperature of the final valve will be Tn plus 1. Here the resistance are clearly written. For the first valve, RTA is written as L by Ka dot A. Similarly for valve 2 and valve 3. So that is it for the class today.